In this example, we're going to find a Thevenin equivalent of the network at the terminal AB. By looking at the circuit, we notice that this circuit only have one dependent power sources. It means that this circuit cannot self-start. It implies that if we use the traditional method by finding the voltage between node A and B, we'll find 0. And if we calculate for the current, we will also get 0. Make it impossible to determine the Thevenin equivalent resistance. This also belongs to case 2 that we talk about in the class. For this type of problems, we need to add an external excitation so that it will allow us to calculate for Thevenin equivalent resistance. So step 1, we are going to add a power source. So over here you have two different choices. You can either add a voltage source to calculate for the current through the network, or you can add a current source to calculate the voltage drop between node AB. Over here we're going to use the first method. So the one we're going to add a voltage source, 1 volt voltage source. So this is 1 volt. Then we can calculate for the current that goes into the network. So this current is I. We can calculate resistance by using 1 volt divided by this current I. At the same time, we know that the open circuit voltage that is equal to 0 volts. Step 2, we're going to solve for current I. So you have different ways that you can calculate current I. You can use nodal analysis, you can use loop analysis. So now we are going to use the nodal analysis. So we're going to use nodal analysis. So for you, just pick the one that you are familiar with. So we're going to select this node as reference node, follow exactly the same steps that we did for nodal analysis. Then we define some nodal voltages. So I'm going to call this nodal voltage V1, and I have everything else. So I just need to write a Kcl equation as this node V1. Let's count the voltage leaving the node. So that is a V1 divided by 2 kilo ohms in this branch, plus the current leaving in this branch, that is V1 minus the voltage of 1 divided by this 2K minus the current goes in through this branch, that is Vx over 1, that is equal to 0. At the same time, since this circuit contains a dependent source, we need a second equation. The second equation comes from the description of the control variable Vx, and it will be represented by using the nodal voltages that we defined. In this branch, we can see that Vx, that is simply half of V1, because we have two resistors of the same value in series in this branch. Then we can solve for V1 and Vx. We find a V1 that is equal to 1 volt, and a Vx that is equal to 0.5 volts. Once we get all the nodal voltage, we can calculate the current. We find the current I that is equal to the current breakdown into this branch and this branch. So that is equal to 1 volt minus V1 that is also equal to 1 volt divided by 2 plus voltage 1 volt divided by the resistance 1 kilo ohm that is equal to 1 milliamp. Step 3, find the Thevenin equivalent resistance RTH. Since we have the voltage 1 volt added to the circuit, that will give us a current of 1 milliamp. So we find a RTH that is equal to 1 volt divided by 1 milliamp, that is equal to 1 kilo ohm. So step 4, we can write the conclusion. The Thevenin equivalence of this circuit becomes a resistor of RTH, where RTH is equal to 1 kilo ohm. This is a special case of a Thevenin equivalent because it doesn't include a Thevenin equivalent voltage source.